Let's look at this advanced 2024 question which was asked on SHM on electrostatics. See, we have a circular loop like this, a non-conducting wire is there, circular wire, and there is a charge which is kept fixed on some point of this circular wire. Let's say it was fixed at this particular point. Let's see, the charge given is Q and it has a mass of M. Okay. Now there is another charge which is like a bead. Okay, that means it can pass through this circumference like this. Okay, now that bead or that charge Q, you can say was placed somewhere like this, and now this had an identical charge as that of the fixed one. Now this is doing to and fro oscillations. Okay, by the way, this is on the horizontal table, right? It is a horizontal non-conducting circular wire on which this charge is fixed and this is movable, and it is doing an oscillation like this. Okay, now they are asking you to find out the angular frequency of the oscillations done by this charge, and this charge has a mass m as well. Okay, this also has a mass m and charge is q. We have to find out the angular frequency of the oscillations, right? So let's see how we can do that. The wire has the radius capital R. Okay, the radius is capital R. The first thing you should do is to find out the force that will be applied on this Q. Obviously, right? See, this is repelling this, so this will be gone like this. Again it will repel it from here, again it will go like this, and it will do this motion, right? And it is also given in the question that these are doing a small oscillations, right? Small oscillations means it is like this here. Okay, it's very small angle. We will be dealing with very small angles, by the way. Okay, so the small oscillations are like this, not like this much big, but I have to show you like this so that you can understand the algebra that I am doing, right? So that's why I have to show it like this. Okay, so the thing is, between this Q and this Q there is this distance, and because of that there is a force, right? Because of this Q there is a force in this direction. Okay, so now what I am going to do, I am going to join this with this center over here. This is the radius r again. Let's call this angle as alpha. Now since this is angle alpha, this angle is also alpha. Why? Because this is an isosceles triangle. These two sides are equal, so these two angles are equal. Very good. So now if I draw these components of this force, right, so it will be somewhat like this. This angle is alpha, so this angle is also alpha, so this is going to be f cos alpha, and this is going to be f sin alpha. Now see, if I find out the restoring force f sin alpha, then it is enough for me to find out the angular frequency, because you know that f sin alpha is kx, and from that you can find the k. Okay, now f sin alpha is the one which is the restoring force. It is bringing this charge towards the mean position. This does not have any role. F cos alpha is perpendicular to this, right? So it doesn't have any role. Only f sin alpha is the restoring force. So the restoring force can be written as f sin alpha. Okay, since the angles that we are dealing with are very small, since it is a small oscillation, I can write this as f into alpha, because sin alpha will become alpha for small angles. You know that approximation, right? Okay, now this charge will come all the way up to this, and it will be here. Again, since the angles are very small, so these 2 points, these are the extreme points of the simple harmonic motion. So these 2 points are not very far from each other, but rather they are very close to each other, such that the distance between them has no curvature at all. It is the straight line. It is like between these 2 points, it is just a straight line like this. Okay, but we have to show you like this because we want you to understand the algebra, right? Okay, so now if I drop a line like this to the mean position, let's say the mean position is over here. Let's call this angle as theta, right? And this is the maximum displacement, let's call it as x. And let me tell you again, this is a horizontal distance. It looks like a curvature, but it is a horizontal distance because of the small angles. Now this is the maximum displacement from the mean position, right? So I want to show f sin alpha as some constant times x. Okay, and we will follow up from that. Now theta can be written as x by r. So theta can be written as x by r. Okay, now what is the relation between these two? Then I can be able to write restoring force in terms of x. See, this triangle you can see, these two angles are alpha. So theta will be equal to 2 alpha. Why? Because it is an exterior angle of that triangle. So that exterior angle is sum of the interior angles of the triangle. So theta is 2 alpha. So I can write theta as 2 alpha is equal to x by r. From here alpha can be written as x by 2r. Okay, right. So the restoring force is going to be equal to F times alpha, which is x by 2r. Okay, now what is F? F is the electrostatic force between these two. But what is this distance? Do you know this distance? How to find out that? Okay, so how will we find out this distance between these two charges? What we will do? Drop a perpendicular like this. Now this distance is r cos alpha, and this distance is also r cos alpha, right? Correct. So if I add both of this, we will get 2r cos alpha. So now the distance between them is 2r cos alpha. So F is going to be kq square by 2r cos alpha whole square, right? This is going to be the force, the electrostatic force. But now alpha is very small angle. So cos alpha can be approximated as 1. For small angles, alpha, cos alpha can be written as 1. So I can write it as kq square by 4r square. So directly I will write it over here. Kq square x by 4r square. So it is 8r cube. But k is 1 upon 4 pi epsilon naught. So this will be 32 pi epsilon naught r cube q square x. So this is the restoring force. Now see here, the restoring force is directly proportional to x. That means yes, this is the constant that we are looking for. The spring constant, or whatever constant you can say, SHM constant. Now this is k dash. So I can write this k dash by m as omega square. So if I write this as 32 pi m epsilon naught r cube. So this is, I am dividing it by m. And if I take a square root of that, then this is the angular frequency. You know omega is root of k by m. So this is the angular frequency of this charged particle over here. You will get this answer. Okay. Thanks for watching.